Alright, in this video we're going to talk about gas laws. We're going to look at how gases behave and how we can determine different properties of gases based on condition changes. So first, just a little overview to make sure we're all thinking correctly about how gases are different than liquids and solids. When we think about gases, we want to think about how molecules behave in a gas state versus liquid or solid. So if you look at part C on the very right, we have molecules in the solid state that are packed very close together, lots of interactions, very little movement of individual molecules. In a liquid, they start to loosen up, so we have more movement of the molecules, less interaction. And in the gas state, the molecules are completely separate from one another, and they have a lot more motion, a lot more kinetic energy associated with the molecules, and very little interaction. So when we describe how these molecules in a gas state are working and moving, we can rely on the kinetic molecular theory. The kinetic molecular theory describes predictably how gas molecules behave, and it's based on a few assumptions. First, we assume that gases are made of tiny particles, so this can be an atom or a very small molecule, and these atoms or molecules are in constant motion, so constantly moving around based on their kinetic energy. They are so far apart that there is no force of attraction or repulsion between molecules or atoms, and they are not interacting with one another. The intermolecular forces are not present. Number two, gas molecules are very far apart. They get as far apart as they possibly can. We also assume then that the distance between the molecules is much, much greater than the volume that the molecules occupy themselves. Alright, so this means that we can ignore the volume that the gas molecules or atoms occupy themselves and focus on that empty space in between them. Number three, all the collisions between these gas molecules or atoms as they're moving around in their container are completely elastic, which means that they don't lose energy. So anytime the molecules or atoms are colliding with one another, they retain all of their energy. Normally, when we have collisions between any two objects, we're going to have energy lost during the collision. But we're assuming the gas molecules or atoms are having elastic collisions, so there's no net loss of kinetic energy. Alright, so to further explore this idea of gas molecules moving around, we also want to define that gas molecules are moving in random directions, and therefore they are going to collide with one another and the sides of the container. Because they're having elastic collisions, the total energy does not change. The total energy in a sample then is based on the temperature. Alright, and we're going to come back to that idea. In number 4, the average kinetic energy of a gas is only dependent upon the temperature. So kinetic energy is the energy of motion of the individual molecules or atoms. We talk about the average kinetic energy averaged over all the molecules in a sample, because kinetic energy can change between different molecules even in the same sample. So we refer to just the average over all the molecules in a sample. And that average kinetic energy then depends only on the temperature of the sample. As the temperature increases, the kinetic energy of the sample increases on average. Alright, so we can see that in the graph shown down here. Different temperature readings, so we have 100, 200, and 300, we see the graph shift to the right, indicating more kinetic energy. And we see this in terms of speed. The increase in kinetic energy means there's more motion in the molecules or atoms themselves, and they can move faster. So at a higher temperature, we can see more of the molecules have a higher speed, a higher kinetic energy. As the temperature decreases, the overall molecules get slower because they have lower kinetic energy. Now, this also applies to every single gas under these assumptions. So average kinetic energy of two different gas samples would be the same if they are at the same temperature. Doesn't matter what the gas is. Alright, so here's our further breakdown of this idea of our kinetic energy. So energy associated with our motion of our molecules is equal to 1/2 the particle mass, so this is like the molar mass of the molecule themselves, times the average speed of the molecules squared. Alright, so because the mass is multiplied by the speed, alright, multiplied by the speed here, if kinetic energy is a constant based on temperature, at a constant temperature then, so we're going to say that this is constant at a constant temperature, then we have an inverse relationship between the mass and the speed. So as mass increases, speed decreases. Alright, so what that means is smaller gas molecules move faster than larger gas molecules. The larger the molecules get, the slower they're going to move at the same temperature, same kinetic energy. So we can see that in the graph down here. H2 is our smallest in terms of molar mass, our smallest mass for our gas, and it has the highest average speed. As our molecules get larger, moving up to oxygen in terms of molar mass, we have a smaller overall average speed. Alright, so inverse relationship. As one goes up, the others go down. Alright, so if we look at one type of molecule, like nitrogen atoms, nitrogen molecules, we see that speed increases with temperature. Alright, so as temperature goes up, kinetic energy goes up, speed goes up. Alright, so that's looking at one type of molecule. If we start changing the molecule, then we want to look at the change in the molar mass. Alright, so here's sort of a summary of how this works based on molar mass and speed. So our molar mass is given here on this first row, so H2 is the smallest, then we have methane, and then we have CO2. Kinetic energy is all the same because same temperature, so all of our gas samples have exactly the same kinetic energy because they're at the same temperature. Then we are looking at the molar mass to determine the speed. The smaller the molar mass, the faster the molecules. Alright, the larger the molar mass, the slower the molecules are going to move, even though they all have the same kinetic energy. Alright, so we understand the assumptions associated with kinetic molecular theory. We're now going to look at how some different characteristics of a gas change and how changing one variable can affect the others. So in order to describe a gas, we have to describe a few different characteristics about it, or conditions in which it exists. And they're listed here. We have to describe the pressure, the volume, the temperature, and the amount, or the moles that we have. Because if I change the pressure of a gas, I can then affect the volume that it occupies, I can change the temperature of the gas just by changing the pressure. Same thing with volume. Because gas molecules are very far apart, gases are compressible. So I can change the volume of the gas by compressing it into a smaller volume or allowing the molecules to separate and occupy a larger space. When I change the volume, this affects the pressure and temperature. Temperature can be affected by pressure and volume as well. We talked about how temperature affects kinetic energy. So if I have a higher temperature and I have more kinetic energy of the sample, the molecules are moving faster. They're going to hit against the sides of the container more and with more force, which increases pressure as well. And then amount. Obviously, the more moles of a gas I have, the more volume it's going to occupy. This can also affect how much pressure there is in the container, because that would mean I have more molecules hitting the sides of the container. But we have a predictable model to determine how these values are going to be affected by changing one or more. Alright, so first thing we want to talk about units for a second. Pressure units are given in several different manners. You're going to be responsible for what's in the red box, so you need to know these. And these are conversions between different types of pressure units. So atmospheres, and we're comparing it to millimeters of mercury, and torr. Notice these two have the same conversion values. So 1 torr is equal to 1 millimeter of mercury. Alright, and then 1 atmosphere is equal to 101.3 kilopascals. This is what you'll see more likely than just regular pascals. Alright, these are the ones you're likely to see, so you need to know these conversion factors. Most of the equations we're going to look at, we want to deal with pressure in terms of ATMs. But if we do see millimeters of mercury or torr, we want to be able to convert. Pressure is defined as the pressure that a gas molecules exert on its surroundings from the molecules moving around their container, hitting the sides of the container. That exerts a pressure. So our first of our gas laws are going to deal with volume and pressure. Alright, so here down here in the bottom right hand corner, we're going to look at our 4 different properties. So our first law deals with the first two, volume and pressure, and this is Boyle's law. And Boyle's law says that if we exert a pressure based on molecules bouncing off the wall, then that will affect the volume that we have. Alright. The Boyle's law says that the pressure times the volume for a molecule or a gas sample of molecules will be proportional to or equal to the pressure times the volume under different conditions. So if I change the pressure or the volume, the other value is affected. Now, because we have them multiplied by one another, this is going to be an inverse relationship. As one goes up, the other goes down. Alright? So if I have increased pressure, it's because I have a smaller volume. The molecules are hitting very rapidly and very hard against the sides of the container because they are being compressed together. So a higher pressure means a lower volume. If I lower the pressure, I can increase the volume space. Alright, so at low pressure, we have very little force hitting the wall, and we're going to have a larger volume space. If we have increased pressure hitting the wall, we end up having less space. Now, even though it's an inverse relationship, it is not a linear relationship. So take a look at the graph over here first. So we have volume along the y, pressure along the x. And so what we see is a curve. Okay? Because even though as one increases, the other decreases, we don't see it changing by the same amount every time. And you can simplify this by thinking about, very simple numbers. Let's say I have 10 atmospheres of pressure and 1 liter. Alright, if I drop down to 9 atmospheres of pressure, then I need to figure out how many liters that would be. So that would be 1.1 liters. If I go down to 8 atmospheres, I'm at 1.25 liters. 7. Okay, you kind of get the idea. It's 1.43. Alright, so even though I'm changing by ones for my atmosphere here, I don't see the identical change here. Here it was 0.1. Here it's now 0.15. Here it's now 0.18. Alright, so you can see that there's a different change in the volume despite having the same changes in pressure. So it's not going to be a linear relationship. It ends up being a curve. Alright, so keep that in mind. But the equation is very straightforward. P1 V1 equals P2 V2. So if I have a 2 milliliter sample of gas, and we're increasing pressure from 400 to 500 kilopascals, what is the new volume? Alright, so my pressure 1 was the 400. My volume was 2 mils. My pressure 2 is the 500, and I'm looking for the new volume. Alright, so very straightforward. We're going to multiply the 400 times the 2, and then we're going to divide by the 500. And I get 1.6 milliliters. Now, look at the units we have. Because the pressure units are the same, 400 to 500, they're going to cancel out when I divide. The volume units are going to be the same. So I had milliliters on the left side. I'm going to end up with milliliters for my answer. So it doesn't matter what units you have of pressure as long as they're the same. It doesn't matter what units of volume you have as long as they're the same. Alright, let's look at a concept idea. If the pressure of a gas with a volume of 300 mils is tripled, what is the new volume? Remember, as one goes up, the other goes down. So if I'm tripling the pressure, I'm going to be dividing the volume by 3. So let's fill in our equation so we can see this. So pressure 1, I don't know what it is, times 300 is equal to, the new pressure is tripled, so I'm going to say 3 times P1. What is the new volume? Alright, so V2. So we're going to divide both sides by my 3P1 to solve for V2. So the P1s are going to cancel, and then 300 divided by 3 gives me 100. So when my pressure is tripled, my volume reduces to the third. So that means 300 goes to 100. Second gas law we're going to look at is Charles' law. And so instead of volume and pressure, we're going to look at volume and temperature. So we have a relationship between volume and temperature as well. And this one, you'll notice, is not multiplied together. We're now dividing. This is a direct relationship. As one goes up, the other goes up. As one goes down, the other goes down. Alright, direct relationship means we see the same effect. Now with this one, we do have a linear relationship, and each is changing by the same amount because we have proportions. Alright, so notice we're looking at ratios or proportions between the volume and the temperature. So V1 over T1 equals V2 over T2. And we can also see why this happens. As the temperature increases and those molecules are moving around more, they're going to expand the volume that they occupy. They're going to be pushing against the sides of their container with more force, and if the container is not rigid and is able to expand, we're going to see an increase in the volume. Alright, so here's our linear relationship. The volume of a gas at 100 Kelvin is 30 mils. What is the temperature of the gas when the volume is 200 mils? Alright, so here's our relationship. V1 over T1 equals V2 over T2. So we have 30 mils over 100 Kelvin, and we're trying to find the new temperature, so 200 mils over T2. Now a word about units. You have to use Kelvin. Have to use Kelvin when we're looking at temperature as part of the equation. Since temperature is on the bottom of our ratio, we can see how we can't use Celsius, because if Celsius was 0, can't divide by 0. So we have to use Kelvin for this relationship. So all temperatures are in Kelvin. Our volume can be in liters or milliliters. That one doesn't matter so much. Alright, a couple ways to solve this type of equation. We can do cross multiplying, or you can calculate the left side, multiply by T2, then divide by the value, however you want to do it. We get 666.7 Kelvin. Alright, so we have the same sort of ratio. 30 to 100 is the same as 200 to 66.7. Alright, so let's look at our concept question then. The temperature of a gas with a volume of 200 mils is doubled. What is the new volume? Alright, so we said they're directly proportional. So if I double one value, I'm going to end up doubling the other. So if temperature is doubled, guess what? Volume is doubled too. Alright, so if the temperature of a gas with a volume of 200, let's just plug this in, is doubled, we're looking for the new volume. I'm going to call this 2 times T1. And then in order to solve for V2, I have to multiply by 2 times T1. Alright, so crosses out on this side. Of course, we just have V2. The T1s are going to cross out, and look what I have, 2 times 200. So 400 is equal to my V2. So if I double one value, I end up doubling the other one. Now if we put Boyle's law and Charles' law together, we get a combined gas law. So pressure, volume, temperature changes for a single substance. Okay, so this is single sample of gas with changing conditions. Alright, so we're not changing how much gas we have, we're not changing to a different type of gas, we're taking that same sample and we're just changing conditions. So we're changing pressure or volume or temperature, and we're seeing how the other values change. Alright, so let's try this out. 200 ml sample of oxygen collected at 298 and 97.4 kilopascals. what volume would this occupy if we change to 101.3 kilopascals at 250? Alright, so we're using our combined gas law because we're given information about pressure, volume, and temperature. So initially we have 97.4 kilopascals and a 200 mil sample, and it's 298 Kelvin. Now we've changed the conditions. We changed the pressure, and we're looking for the new volume because the temperature also changed. Alright, so if we look at what happened, pressure's going up, so if pressure goes up, we know volume is going to go down. That's that inverse relationship. Temperature is also decreasing. So if temperature decreases, volume decreases because those are directly related. So we expect volume to be less under the new conditions. Alright, so again, there's a couple ways to solve this. Everything on the left side is a real number, so you can plug that into your calculator, then multiply by 250, then divide by the 101.3. So I get 161.3, and this is milliliters, because that's what we started with volume. Okay, so it is decreased like we expected, because the pressure goes up, so volume has to go down. Temperature goes down, so volume also goes down. Alright, what would happen to the pressure of the gas if the volume was tripled and the temperature decreased by half? Alright, so we're going to say initial conditions. We don't have any numbers, but we're just going to name them based on their variables. And then we're going to look what happens to these conditions. So we're trying to find P2. The volume is tripled, so I'm going to call it 3 times V1. And the temperature decreased by half, so I'm going to call it T1 divided by 2. Okay? So now we want to try to isolate P2. This is the variable that we're solving for. So I'm going to multiply both sides by T1 over 2. That means all of this is canceled out on the right. That means my T1s are canceled out, leaving the 2 there on the bottom. Alright, and then we want to divide both sides by dividing by 3 over V1, or same thing as multiplying by 1 over 3V1, however you want to look at that. Alright, so it crosses out on the right side, so we're left with P2. V1 crosses out over here, so I'm left with P1 over 3 times 2 is 6. Alright, so it means that P2 is 1/6 of P1, or it means that P1 is 6 times P2. Okay, so that means our pressure is decreasing to 1/6 of the original. Volume is going up, so we know pressure is going down. Temperature is decreased, so that also means that pressure will be decreased, which we're about to look at. Alright, and as promised, Gay-Lussac's law, pressure and temperature. Also a direct relationship, very much like our pressure like our volume and temperature that we just looked at. So it looks exactly the same, but instead of volume and temperature, pressure and temperature. And we still see this linear relationship. As one goes up, the other goes up, because we have proportions again. Alright, so we're going to look for the pressure change. a constant volume of gas at 1 atmosphere is heated from 20 to 30. So we have pressure 1 over temperature 1 equals pressure 2 over temperature 2. Remember, temperature must be in Kelvin for these calculations. So we're going to start with 1 atmosphere over our 20 degrees plus the 273. Alright, so turning it into Kelvin, we're looking for P2. Turning the other one into Kelvin as well. Alright, so we end up with 1.034 atmospheres. So we're increasing the temperature, which means our pressure should go up. We're not increasing the temperature that much, so we get a very small increase in pressure. Alright, let's try one more. Initially we have 0.5 atmospheres, and we're looking at Kelvin, of course, 25 degrees Celsius, 298. And what is the new pressure if we go to 125 Celsius or 398? So our pressure ends up being 0.668 atmospheres. Alright, increasing the temperature increases the pressure. The more we increase temperature, the more we increase pressure. Direct relationship. Right, our last one of these simple gas laws is Avogadro's law, which now relates our volume and our moles. So the more moles of gas we have, the more volume that occupies. Okay, and that makes sense. And that is also a direct relationship. So again, we're looking at our lovely ratios over here. As one goes up, the other goes up. As one goes down, the other goes down. Okay, so linear relationship. N is our symbol for moles that we're going to use to represent the moles of gas. And we're going to see that in other equations as well. So this assumes we're keeping pressure and temperature constant. Then we can see this relationship between moles and volume. Alright, we have a 25.5 liter balloon that has 3.5 moles carbon dioxide, but the carbon dioxide is leaking out. We lost 1.9 moles before we were able to reseal the balloon. What is the new volume? So volume 1 over N1 equals volume 2 over N2. So we have 25.5 liters and 3.5 moles at first. We want to know the new volume. And then here we have to calculate how many moles are left. So we started out with 3.5, but we lost 1.9. So we need to calculate how many are left, and then we can find our volume. So we get 11.66 liters. Alright, so since we lost some moles, the number of moles decreased, the volume is going to decrease. Alright, one more time. This time we're given a lot more information. A vessel contains 2.98 moles at 35.1 Celsius and 2.3 atmospheres in a 32.8 liter container, so there's our volume. How many moles are in a 45.3 liter container under these same conditions? And this means constant pressure and temperature. Since my pressure and temperature are not changing, I'm just going to use Avogadro's law. So I have 32.8 liters and 2.98 moles equals 45.3 liters. And I'm looking for moles. Alright, so either cross multiply or solve the left side and then divide the 45.3 by that number. Either way, I get 4.12 moles of the gas. So as the volume increases, the number of moles is going to increase. It's directly proportional. Alright, so here's our summary. We have 4 different simple gas laws. Boyle's law relates pressure and volume. Pressure and volume are inversely related. As one goes up, the other goes down. Charles' law relates volume and temperature, which are directly related. One goes up, the other goes up. And in similar fashion, Gay-Lussac's law with pressure and temperature. As one goes up, the other goes up, so direct relationship. And then Avogadro's law, which looks at volume and moles. As the number of moles increases, the volume increases. Combined gas law puts Boyle's and Charles' law together, so we can look at those 3 variables as they change. When conditions change, we can predictably calculate what the new values will be. Alright, so let's look at a couple of final examples for these laws. Sample of gas has a volume of 3.5 liters and pressure of 0.610 atmospheres at 10 Celsius. What is the final temperature, so we're solving for T, if the volume of the gas changes to 8 liters at a pressure of 0.19? N is not changed. So we are changing the volume, we are changing the pressure, we are changing the temperature. Since we are doing all 3 of those things, we're going to use the combined gas law. Alright, so if we put in our pressure, we have 0.61 times 3.5 liters over, we're starting at 10 Celsius, but remember, we have to have it in Kelvin. And then on the right side, we have 0.19 atmospheres for pressure, 8 liters for our volume, and we're solving for T2. Alright, so we see the pressure go down. Pressure is decreasing. We see the volume increasing as we would expect. And so what should happen to the temperature? Well, if the pressure is going down, the volume is going up, that might be enough to cancel it out. We may not see a huge change in temperature, but we need to calculate it to figure out what's actually happening. So I would recommend solving the left side. All these are real numbers, multiplying by the T2, and then dividing by these numbers. So when I do the math, I get T2 is 201.6 Kelvin. So temperature goes down because pressure is decreasing dramatically. Alright, one more. The air in a 2-liter tank has a pressure of 1.3 atmospheres at 50 degrees Celsius. What is the new pressure when the air is placed in a tank that has a volume of 450 mils at 20 degrees? So we are changing volume and temperature, looking for pressure. So again, since it's all 3, we want to fill that in. 1.3 atmospheres, 2 liters, and 50 degrees Celsius. Again, we're going to add that to the 273.15. So we get 323.15 for Kelvin. And then on the right side, we're trying to find the new pressure. I need to convert my to liters, so my volume is going to be in liters because I had liters on the left side I need liters on the right side, so make sure your units match. And then we fill in our temperature. Alright, so we're solving for P2. And because we see the volume decreasing, we're going to see the pressure go up. So 5.24 atmospheres. Alright, so we can look at changes to pressure, volume, temperature, or the number of moles and determine what gas law is applied. If we're only changing one or two, we could probably simplify it to one of the simple gas laws. If we're changing multiple variables for the conditions, we have to use combined gas law.